I'm Rich Landau.
Oh, is it okay to record?
Yes, go
Okay,
ahead.
good.
I'm Rich Landau from Goddard's Flight Software Systems branch, code 582, and I am the Core Flight System Product Development Lead. So cFS, as it's commonly known, is a flight software framework. So let me jump in. I'll start with a quick what is flight software. I think this is review. We already saw from F Prime and some others. But typically when we're talking flight software here at NASA, we're talking about software on a spacecraft. So it could be a bus, a spacecraft, an instrument, a payload, but it's typically not avionics. We don't really focus on aircraft in our group. And it kind of controls the entire mission. So if you don't have your flight software, you really can't do anything. It talks to all the subsystems, and it's the only thing that can be changed once you're on orbit. So it's really, the kind of the heart and brains of the system where it's going to enable your mission, and it's going to be the only thing that you can change later, kind of going back to what Joshua was talking about this morning. So you can see on the left here, a couple missions that would be running flight software, launch vehicles, something like James Webb, landers, but typically not aircraft. So what is cFS? So Yvonne kind of stole my lead a little bit. I think he already presented a version of this chat. But cFS is a flight software framework. It's more than a flight software framework. It was actually named by the NASA International Software System Interoperability Standards Group, which is quite a mouthful, as the flight software framework for international collaboration. Gateway is using it and requiring all their international partners to use it. So it's propagated kind of far and wide beyond anyone's wildest dreams. And it was the Software of the Year award winner in 2020. So you can see a diagram on the right here of what makes up cFS, and I'll go into all these layers kind of in more detail, even though Yvonne already stole my presentation here. Just kidding, Yvonne. But essentially, it's got modular software applications in the blue, light blue, kind of toward the top, that provide a lot of capability that most missions will need. So you can kind of take applications that have been built, they're flight proven, TRL 9, take them off the shelf, put them into your mission, configure them, they'll just work. Then it's got core services that every mission is going to require. So that's things like, what time is it? How do I configure a generic application? Starting and stopping applications and services, communicating between them. That's the core flight executive layer. And then it's got portability. No matter what platform or operating system you're running, a cFS is just going to work without having to rewrite your code. So that's that platform abstraction layer. And then it's got a bunch of supporting tools around it. So cFS is open source. I have the GitHub link here. It was open sourced in 2011, so it's been quite a number of years now. It's evolved over time. It's been more of a slow and steady iteration. There's some more kind of moonshots that we're working on that I'll talk to a little bit at the end. But with so many missions using cFS, and we'll talk about that, you have to be kind of careful with your maintenance, just like in the Linux kernel, right, where you change the wrong thing and break an active mission, and it's a problem. So here's what a typical cFS deployment looks like. So that blue box in the middle, that's the software bus component of the core executive, which routes messages between all the other components. So you can see the stuff in blue. Those are kind of the core services that cFS, the core flight executive portion of it, CFE, provides. So I just talked about that. And then the bubbles in pink, those are your modular applications. Those can be plugged in or taken out depending on your mission needs. And then it provides a streamlined API so that your missions can develop their own applications for talking to a piece of hardware, for monitoring some particular mission-specific thing, and plug right into that API, be able to use all the functions that cFS provides. And what's nice is groups that use cFS, they know these interfaces. They go from mission to mission to mission. They know what the style is going to look like. They know the expectations. They know the tools. It makes that learning curve very, very flat for people who've been using it for a while. So I want to talk a little bit about usage. So cFS has been used by over 40 NASA missions over the past 20-ish, 15-ish years. 6 NASA centers are using it. We actually have a steering committee now where each center has representation. We meet monthly and talk about, where is cFS going? What do people want? What do people need? One of the challenges something like cFS has is it's open source, but not everyone contributes to the open source. Some people grab it for their own mission, they do their own development, they kind of keep that to their group and they build on it. So you've got a lot of forks all throughout the ecosystem. So we're trying to be intentional about this was built as a reuse tool. Let's make sure everyone is in the same room talking, and maybe you built the same thing as me. Let's standardize it, bring it into the core. Not everything can be open source, but things that we can, we try to do. And so we're trying to just be a little bit more intentional about how do we take this capability that's been used across all these centers, industry, et cetera, and bring it into one place for everyone to use. So some flagship missions, I mentioned Gateway, all their modules have to use it. So Gateway is a manned mission. So we were talking earlier about the software class. So they've certified cFS to class A for human rated. The framework itself is not class A certified, but we say it can be certified to class A because certification depends on what platform you're running on and all these other things. So we have, a lot of those tests and artifacts built in. And, we're constantly trying to make it more approachable and have some of these forks kind of pulled together into one product that has everything. Roman Space Telescope, which is launching in a couple years, the successor to James Webb. And then Mars Sample Return, it's going through a re-architecture right now, but the capture, containment, and return system that Goddard was building was using it. The Mars Ascent Vehicle rocket that Marshall was using it. So a lot of high-profile missions have all used cFS, and since it's been flown for a long time, there's a lot of trust there that it's going to work. And then since it's open source, there's also a lot of private companies and universities using it. We get outreach all the time. I emphasize that we know of because it's open source. People come and use it, and to a smaller scale, it's like saying who uses Linux, like right?
We know.
But sometimes we get some public shout outs, which we always appreciate. The CTO of Intuitive Machines after the Odysseus lunar lander credited it. If for those who don't remember, they had a failure with the landing LiDAR on the way into the moon, and they had to reroute a payload LiDAR to be able to use it to do the landing. And they basically said, thank goodness for cFS that we were able to do the reprogramming so quickly as we were approaching the moon. So that was a really good shout out from them. And then a bunch of foreign space agencies use it, some in collaboration with us, some just because they want a good starting point, and cFS is kind of the standard that we know of, could be more. And I mentioned a Roomba just because people always ask, like, what's the craziest thing that people put cFS on? I've heard stories about toasters, Roombas, all sorts of crazy stuff. But if you look at this chart on the right, this is kind of a breakdown of how it's been used, again, based on our data that we know of. Primarily spacecraft and payloads make up the bulk of it, but everything from rovers to spacesuits to launch vehicles, balloons. What's nice about cFS is it's so modular that these concepts are really, they're designed for space, but they're really so general, you could do them for pretty much anything. So it's just a really good kind of baseline platform for doing this type of embedded development, kind of beyond just space. So some of the benefits, I mean, some of this is pretty obvious, like why build things that are reusable, right? But you reduce defects. If you start from scratch, you build your code, you have X number of bugs. Well, if you're starting from something that's been flown 20 times, we've ironed out all those bugs. We haven't found all of them, but I like to say we're pretty close. They've done some modeling. I don't take credit for these numbers, but compared to clone and own, they say it reduces cost by at least 50%. I've seen higher numbers too, but I like to be conservative. That's not versus starting from scratch. That's versus, what Michael was talking about earlier from with F prime as well. Starting from your previous mission and taking it and changing it. Then let's say now you're using, this version of Linux instead of that. Things change under the hood. It breaks things. If you can abstract all of that, you're saving a lot of time and money. And then I already mentioned the feel is shared. So at NASA, our missions can last 50 years was an extreme example that Joshua mentioned this morning, but regularly 10, 20. And if you're working on, sustaining 10 of them, or if you just got done developing one, you're moving to the next one, you don't want to be learning from scratch. So that's a real benefit. And then because of these things, it lowers project risks, makes schedules a little more predictable because we know, hey, if I want to do X, this mission did it with cFS, it was similar. Let's use those numbers. Obviously, I don't like using Slock as a starting point, but it's one of the better things that we have. And then standards, we use a bunch of standards in cFS, the CCSDS. I'm not going to try to remember what the acronym is, but they have the space packet protocols that make up our entire messaging framework on board, kind of define how to send commands and receive telemetry from an application on board. And then again, now cFS is the standard for flight software frameworks being used across all these mission partners for Gateway and others. So we try to lean into standards as much as we can because we don't like, rolling our own thing when there's a standard that people have agreed on to do it better. So I want to jump through some of the layers of cFS, starting with the operating system, which I'm sure is why a lot of you are here. So we have, the stuff in gray. This is stuff that a mission will develop special for them. And then the green here is this third party. It says real-time OS. So I will admit, Linux has been kind of something of a second-class citizen for cFS. cFS's bread and butter is real-time embedded systems running on VxWorks, RTEMS, free RTOS, stuff like that. I think there's some potential for that to change. We'll talk about that a little later. Yes.
The potential for Linux use, definitely that's what we're all here. I'm just curious, are you actually looking at Zephyr at all or not?
So I've heard of missions using it in other contexts.
Okay.
I don't know if it's been used with cFS at all. It's not something that we've been looking at bringing into the main line just because there hasn't been a lot of demand or funding for it. But we want to support as many OSs and platforms as we can.
Sure.
It's just resources are very much a challenge for everybody, but for us particularly.
Okay,
Zephyr has a POSIX interface.
yes,
Okay, it's supported. It's good enough.
it's mostly all, it's mostly there, it's just a question of which feature to use it.
I hear a volunteer.
Oh,
So we do support PC Linux for desktop development, similar to what Michael was saying with F Prime. You know, you want to be able to build it on your computer, run it, see that it works before you test it on your embedded environment. So we have that built in, that's the default for the core. And a lot of groups have used Linux operationally for CubeSats and whatnot. I think Michael's group actually is probably the best example of this, at Goddard, at least that I know of, is running it on Linux operationally. Our group has been more on the real-time side, but we're trying to get all that together. And, you know, my long-term vision, I'd love to have an embedded OSL implementation. We'll talk about that, that can run kind of a real-time flavor of Linux. I'm not going to get corrected on the specific terminology, but we want to make it more of a first-class citizen. So that brings us into the platform abstraction layer. So again, the real goal here is that stuff written up at the application level doesn't want to know about what operating system you're using. So the POSIX API is becoming a standard. We're using that more and more when we can. Even, you know, operating systems that historically have not supported POSIX, newer versions are starting to, and we're starting to step up to them. So maybe some of this will be smaller and smaller over time, which is, again, if we can lean into a standard, that's fantastic. But there's always outliers, and platforms are always different. So, you know, when you have your chip running an operating system, what are the memory ranges? How do I configure it? How do I do all those things? So we break that into two sections. So on the left is what we call the OSL, the operating system abstraction layer, which is just kind of mapping your standard CFE API to, you know, the Linux implementation, the XWorks, everything kind of has its own custom that, again, we're trying to consolidate where we can. And then the platform support package, which is I'm running Linux on the HPSC platform that Joshua was talking about earlier. We have a custom PSP that would define how all that is set up. And then nothing above the stack needs to care about that. So again, trying to move toward POSIX where we can, since more and more people are supporting it, which we love to see. And then there's the CFE. So this is the 5 services that pretty much everybody needs. The executive services is the first thing that starts when CFS starts, and it loads all the other services, initializes them, configures the system, loads the applications, provides utilities such as memory pool abstractions, that sort of thing. Event services for logging and downlinking events. The software bus for routing messages between components that uses publish subscribe. So you know, an app can come in and say, hey, I want to hear about message Y, and I'll spit out message X, and the software bus will do all that routing under the hood for you. And then table services to do dynamic configuration and reloadable configuration. So these are the most common software changes we do once we're on orbit is, hey, we have all these parameters configured. We need to change, you know, this particular one. We'll go upload a new table, and then we're not really messing with the software. We're just messing with the configuration and reloading it, which is a lot safer. And then time services, which is stating the obvious. And then finally, application layer and tools. So the applications are very, very modular. So again, we provide those teal ones to, they're all open source on the NASA GitHub. They're all in their own repos. You can pick and choose what you need. We're actually working on building a bundler tool is what I'm calling it, which is kind of like a GUI front end where, hey, you're a new mission. Do you need this? Do you need that? You can kind of pick and choose what you need. We'll have links to everything, descriptions, and kind of like a menu at a restaurant, right? To say, you're building your flight software. What do you need? What can we provide for you? And then you would go and add your own custom sauce after that. We don't have that today, but that's something that we're working on getting out there. But we provide all these functionalities, and then all the stuff in gray is just an example of what a mission might develop, right? If you have a solar array that you need to talk to, you would have an app for that. If you're, you know, ingesting commands, what protocols are you using under the hood? You know, we're again doing efforts to commonize some of that stuff and be able to say, well, you know, we'll have a configuration flag if you're using TCP, UDP, spacewire. You know, you set that at compile time, that's the flavor that it'll implement. And then you don't need, so all these things that are in gray, we're trying to make some of them teal where it makes sense, just based on the resources that we have. And then we have tools above it, things like unit test frameworks built in, performance analyzers, The ability to generate a shell application is something that we just finished that we plan to open source soon. Kind of a dummy ground system. It's nowhere near as sophisticated as a real one, but it lets you send commands, receive telemetry, see how things look. It's all tied together with CMake, so that all kind of comes free out of the box. So that's CFS in a nutshell. Before I move into the future, does anyone have any questions? Yep.
What's the linkage between all these? Is this like C dynamically linked or what's?
Yeah, it's a good question. So right now, everything at the core flight executive level and down through platform abstraction gets compiled into a single like shared or static library. And then all the stuff at the application level are all dynamic libraries, and they get dynamically linked in by the core flight executive when it kind of has a config file that it reads, say, what apps are you loading? And it goes and it finds those libraries.
They're all in the same address space?
They do today, and that's something that we want to change, and I'll talk about that in future section a little bit.
Okay.
Yep.
I can also read the application layer, give us a few examples, the applications.
Sure, yes, sorry, might be.
Listing there.
Yeah, it's a little small. So one of them, CFDP, that's how you transfer files, the CFDP transfer protocol to and from the spacecraft. There's checksum, check a hash of something, make sure your file didn't get corrupted. Limit checker, so that's where I have a telemetry point, make sure it's within these bounds, otherwise execute this command. Stored command, which lets you set up a sequence of command and executes them at various times. And that's tied in with the limit checker to be able to do fault responses. File management, scheduler app to be able to trigger events on various frequencies. Software bus network, which is how you can communicate between separate instances of CFS. So if CFS is a single memory space right now, you can run multiple and connect them with SBN. So that's been kind of the current paradigm that we're looking to get away from. Health and safety, those are just kind of a few examples, but they're things that most missions want most of these, but you don't always, and we let you kind of swap them in and out.
So your code today will probably use the doc string or some documentation, right, provide to your developers.
Mhm.
So have you considered using this documentation approach that those guys showed today?
I
Really,
was,
approach together, the activity, because
I was taking mental notes. I think like most people, we keep our requirements separate from the code. And then you update the code, you have to remember to go update the requirements. How do you verify it? We have these functional tests. You have to update the functional tests. It's tough. So we could talk more. I'm very interested in what you're doing.
Yeah, and I'm gonna see if we can bring this together under a work group, SPDX work group.
Great.
For Chris, Mel, I was gonna ask you, is there a Yocto meta layer for any of this at all?
So under the Linux support for the OSL, right now it's just PC Linux. Projects have built their own Yocto implementations of it. None of it is like formally in CFS. CFS is the framework and people build their own pieces. I hope that whatever comes out of this group, there's a formal space version of Linux that we can include an OSL for that and make that the official one. But right now, Yocto is kind of not officially part of anything we're doing. You have to kind of add your own custom piece in here.
You get a lot more uptake, be a lot easier to use it and incorporate. I think that's fun.
There are a couple of challenges. A lot of folks will look at CFS as an application that's designed to be compiled separately from a build system such as Yocto. And that ties in with the separate dynamically linked applications such that they're dynamically linked so that just the apps could be uploaded to the spacecraft, for example. So there's a little bit more, there's a few more conversations to be had.
Yeah, and the other thing there is we want CFS to be independent to the extent possible because not everyone wants to use Linux. Some people want to use real-time operating systems. And if we tie to any particular system that can't scale across, then we have to start maintaining a bunch of different things. It becomes tricky.
And there are a couple of tweaks that were made in, and I don't want to use the word tweaks, but and I don't want to use the word hacks either. Let's just say CMake was used very creatively in a good way, very good way. That
Well, Big Ben can wrap any build system. So we can
Yes.
wrap right around.
There-
it. Keep going.
there are some issues with the way native tools are compiled in cFS, there's a table.
We might want to take this offline.
Yes.
Why don't you finish
Yeah,
that?
yeah.
We can talk about it after.
Thanks. So about the future, so I want to talk about Linux a little bit. Again, it's been kind of a second-class citizen. I'm not going to hide that. But there's two big things that I think is going to bring it more mainstream in cFS and, embedded real-time flight software land. One of them is, preempt RT being in the main line. If it gets more adoption by missions, then there's going to be more demand for us to formally make an OSIL for that. Right now, it's been such a Class D CubeSat type thing. People just throw what they have in there. No one's asked us, hey, can you build an official one that can be certified or anything like that? Maybe this will change that. I think time will tell. The challenge is, we still have these processors, thanks to the radiation effects that Ted was talking about earlier. A lot of the processors we use, they're not very powerful to say the least. So, the mission I was just on a year ago was 16 megabytes of RAM and 8 megabytes of storage. So you have to fit the kernel and everything else in there. Now, I'm not a Linux expert. I understand the kernel can get pretty small. I'd be curious to know versus that, talk with me later. But, we got to keep it small.
That's what she meant by Zephyr.
Okay.
Yeah, and
You can hit that.
you can.
Yeah.
I hit
Yeah, it's about 3 megabytes comfortably,
Okay.
but
Yeah.
but if you need to get smaller than
Yeah.
that, that's to talk to Zephyr.
But do those processors have
Do they have what?
MMUs down? So,
Most of them don't. Some of the newer stuff.
yeah,
Okay, there.
That's
There's non-MMU in Linux, but it's not very much.
yeah, it's.
At that point, it's time to go to that side.
yeah. So that's one way is let's use Linux for our real-time command and data handling with the real-time stuff, right? On the other side, there's let's use an RTOS as we always have for our CNDH, but let's use Linux for parallel processing. And Joshua was talking very well this morning about, HPSC, and it's got 8 cores. Historically, we've had 1, sometimes 2. So this is kind of a notional architecture that I have up here where I think a lot of our future missions, they're going to have their RTOS take up a few of the cores up here and do all your standard day-to-day stuff, and then have a second core where it's kind of hard to read on here, but this is like an AI inferencing kind of notional application where I want to have 2 of my cores do my RTOS CNDH and then have 6 of them just crunch on machine learning algorithms all day processing data. And that can run Linux. And we can talk with, SBN today, we could set this up using WorldGuard in between. So stuff doesn't propagate or, trust zone or whatever we were talking about earlier. So stuff doesn't propagate between the two. So I think this is going to become a really common architecture going forward. So
What about classification? Is it possible that Linux core be classified like say D while the RTOS core be classified C?
we'll have to call Scott Tashaport back in, but that is really my hope, because if we have to classify all this stuff to the highest level, it's going to be really tough. But I think it would depend on what you're using the AI for, right? If you're steering your spacecraft with AI algorithms, probably not. But if you're just processing data and it's not gonna, ruin your mission if it goes wrong, I assume that's how it would flow. So a couple more things that are not directly Linux related, but they really tie into the big ecosystem. Wanted to talk about it. What else are we excited about? So memory safe programming languages. I know there's been a lot of debate in the Linux community about Rust. I don't know how you all feel. I'd love to talk offline. But
So Linus has actually said officially that Rust is the future of Linux.
great. I'm a big fan of it personally, and I'm trying to convert people. There's very few people at Goddard who are even know it, let alone have an opinion on it. We're trying to change that. So I have an IRAD that I'm working with some folks to try to convert CFE, so kind of that middle layer, to Rust. So that'll provide a Rust API for applications. So apps can now be written in Rust, get all those safety benefits. But it's also going to provide a backward compatible C API. So all the apps that people have developed over the past 20 years will continue to work, as they have for 20 years, no change. I mean, obviously the implementation will be different, going back to what we were talking about earlier with the requirements. So we'll have to re-verify everything that we use, which you have to do every mission anyway. But this way we get a safe core with memory and concurrency safety. We get safe apps for anything that wants to use Rust with that Rust API, but we don't throw away the ecosystem and start over. We kind of blend it in, which is similar to, I think, how Linux is doing it.
Can you get rid of Cardinal?
I'll make some calls.
Yeah.
And as well as I'd love to have dynamic libraries. Anything else? Those 2 things.
Just
Those are the 2 things I want to just go on steroids.
So moving over to the right, distributed communication and computing. So we have another IRAD in work to support data distribution service. Yvonne was just talking about Space ROS and ROS 2. It uses DDS under the hood. So there's really 2 goals of this IRAD. One is to talk to ROS. He mentioned a couple of bridges that other people are working. They're more interface converters. This is, let's replace messaging within cFS to use DDS. A lot of questions, performance, overhead. We need to verify all that. We're not there yet. But that's one benefit as we talk to Ross, but the other real benefit is now we have stuff, talk about stuff across two partitions and RTOS or Linux. Maybe we have stuff on different processors, maybe different subsystems. Now that can all act as one big flight software instance and all talk to each other over DDS, and they don't need to know each other. And it can be a lot more of a dynamic system. And this DTN project, delay tolerant networking, trying to build a network in space. If you can then scale that up and have publish subscribe messages between spacecraft, there's a whole lot of potential there. So that's another IRAD we're working. And then more powerful spaceflight hardware in the bottom left, Joshua talked about HPSC. That's really what this is referring to. It can do a whole lot that enables a lot of this stuff. We're kind of getting out of the realm of 100 megahertz clocks running one core, which is great. And then onboard AI is kind of the next natural step of all that. Now that we have this ability to do AI processing on a spaceflight hardware, now we can do science processing on board. We could put an LLM on board. There's been a lot of talk about, well, humans are going to Mars. They won't have the experts with them. What if something goes wrong? LLMs can, learn the systems, learn the instruction manuals, help coach them, be able to maybe do onboard autonomy one day, do it in a sandbox very safely soon. Hope no one asks us to classify it to Class A. I don't know how that'll work. But there's a lot of potential here. So those are just some of the other things that we're looking at bringing into cFS, which again, we're not going to drop them into the main line one day. They're kind of side projects right now, but you always have to be looking forward. We don't want to be stuck in the realm of one core processors forever. We want to be able to kind of get with the modern age of space hardware and software. So I think that's my last slide. Is there any questions? Yep.
Got one.
Are you all
there.
looking at running time sensitive networks in the future as well?
Great question. So we actually have a customer already about to be using cFS with TSN. So we're doing some investigation with them as to what that will look like. And then HPSC, which is coming out, is using TSN as its primary method of networking. So a lot of it is in the hardware and the protocol layer. What we've been trying to ask ourselves is what is cFS's role there, right? Besides sending Ethernet messages out onto a network. Can we specify the quality of service on a per message basis in the app? Can we configure the networks that boot up, that sort of thing? But we're still very early in figuring all that out.
And part of the cousin of TSN or predecessor TTE is heavily used in many of our human spaceflight endeavors. So the gateway system that Rich mentioned that's using CFS currently uses TTE Ethernet. So they have not yet adopted TSN just because from standards perspective availability of parts, that's not yet sufficiently.
Thanks.
Anything else?
There's a question on chat. I'm going to ask Matt to unmute to speak.
Sure. Has anyone looked at integrating Airing 653 together with cFS on Linux? And I'm curious because it would open an opportunity towards like mixed class criticality and rigor use cases. It would also standardize, we're all going to have to do like interference analysis on multi-core systems. And maybe we might get some portability with avionics and other applications, in sort of parallel industry type of way.
Yeah, it's an interesting question. It's not anything that we've looked at yet. Typically, our systems are more preemptive. So it's
Okay.
something people have brought up before that we definitely want to spend some time with, but no one's come to us and said, hey, we're doing this and help us with this, which is usually, we have limited resources. We have to kind of steer it toward what people are actually asking us for at any given time. So if someone comes to us and says, this is what we want to do, yeah, we're going to look into it. But it's something that's interesting right now, but kind of on the peripheral of our radar, if that makes sense.
Okay. Makes sense.
Say again?
Some of your HPSC work may touch on that.
It's going to touch on everything. Yeah. I think I saw one more question.
Yeah, I was just wondering, you were mentioning that you have requirements and you're taking them in Node tool. It's mainly then CFS open source part. The source code is the design architecture. How much is open source? Can I also find requirements somewhere? Would be the concrete question.
So the requirements on a per app basis are in the repos with the apps. So you can go in and get them for CFE for each of the apps. What missions typically do is they have their own requirements and then they will have to show how CFS meets them, right? So CFS is not, going back to what I was saying earlier, it's not class A or even class B. It's kind of framework code that other projects have to come in and certify. So we have requirements to kind of know what to expect, and because, that's what you're supposed to do. But we don't have like formal methods of testing against them. But yeah, there are requirements out on the repos just in like CSV files. It's not anything super fancy. And then there's some design stuff that has been, there's like, if you Google it, there's been some public publications about, trainings and whatnot that go into the design a little bit, but our formal design documents, I think, are only internal. I don't think they've been released, but I have to double check on that.
You'll actually find the Word docs, just put in the repos.
Okay.
Yeah, there's a lot of stuff in the repos.
One question here, is there any public roadmap for releases for CFS?
So we've actually been trying to do a much better job at the public facing side of things. For a while, it was like engineers love this and they're working on it, and there was no thought about image. So we have a program manager, Ashok Prajapati, who was going to be here. I think he was busy in training, but he's just put up a new website. So if you Google CFS Goddard, you should come across the new website. It's got some content on there. The problem is a lot of the stuff is like that we're doing for customers. We're still working out whether it can be open sourced or if some of it's going to be internal and, kind of on a agreement only type of thing. There's going to be a line somewhere where some capability is not going to be released. And so I think that the public facing roadmap is only going to be a subset of it. And I can't remember if it's on the website, but we also have some stuff in the README if you go to the GitHub for CFS. So there is some stuff up there, but I wouldn't say that it's necessarily complete.
Last question, is there any governance structure for the project?
Sorry, any what?
Governance structure for the project?
The governance on the project.
Yeah, so I mean, the PM is the, point of contact, kind of authority in charge of the project, and then the team develops under that.
So the team is all internal NASA people at this point in time. There's no external
Oh, so
contributions
I see. So yeah, we do get external contributions
with
and
the CLA.
with the CLA, and we have, sorry if that's bad news. We have a weekly configuration control board where the team internal meets and dispositions them and merges them in. Due to resources, we have like probably 50 open PRs, and we get through 2 or 3 a week. So we've got quite a backlog, unfortunately. If there's anything super critical, we try to jump on that if people reach out to us, but if you open a pull request, it may just sit there for a little while. So you're welcome to reach out to me directly so we can help prioritize stuff. We've just been kind of drowning due to, we actually didn't have much of a team for a couple years during COVID, and we built it back up over the past year or so. So we're trying to get caught up on our backlog while developing all the new stuff on a lean team. It's quite a challenge. So
Welcome to open source.
yeah, doing what we can. All right.
Thank you.
Oh, yeah.
You mentioned that requirements were in the repository of CSV and Word docs. Is that how you guys formally see any requirements or those standards? Something like
So we have requirements in Jira internally, but again, our requirements are not like emissions requirements. So emission will typically use doors or something more formal and point to our stuff. But right now we have it in CSV, we have it in Jira, but we don't do a formal like doors or anything like that on our team. We're a little more agile, kind of just trying to.
Mitch, would it be fair to cast the requirement whatever you're tracking are your CFS software requirements as opposed to NASA's requirements for software, or emissions requirements for capability?
Yeah, and something we want to do a little bit better of is having like a main matrix mapping the NPR requirements to what we're doing and buttoning all the things. A lot of the time, since we're framework software, we say, well, here's what we're providing, missions take this for free, but you need to verify your stuff against the NPR because you're the one that's flying this stuff. We're trying to do as much as we can, taking that stuff, not necessarily from the missions, but doing it ourselves first. So we say, hey, you can double verify this, but we already proved that we have, 100% CDC coverage and static analysis and all this stuff, and provide those artifacts. So we're not there today, but we're trying to do more and more of that as we can.
Okay, well, I think we're going to be on the break now for a few minutes, but before, and as we break, if everybody